So suppose that we are going to take 3 steps and we flip a coin to decide if we step left or right. Okay, so we're going to start in the middle. So here's our starting point right here. And if we flip the coin and we get heads, we step right. So we step once. Okay, so our goal is to figure out what are all the possible positions we could go. Okay, with stepping left or right or heads and tails being equally probable. So it is possible, one possibility is to get 3 heads in a row. So you step left once, step right, step right, step right. There's only one way that could happen. Okay, so 3 heads in a row, or in other words, we step right each time. Well, you can see here the rest of the possibilities. You can step right, right, and then left. Okay, or right, left, and right, and so on and so on, all the way down to left, left, and left. Okay, now we see that if with those equal probabilities of taking a step left or right, these are all the possibilities, then the question becomes, what's the probability of being at some position? Okay, we see to get to 3, there is only one possibility out of all 8 of these possibilities. So that means the probability of getting to 3 is just 1/8. Okay, likewise, getting to -3, there's only one possibility. And again, 1/8. But getting to 2, okay, there's no possibility. None of them end here. Okay. All right, this one goes there but steps back. This one never gets there. Okay, nothing ends here. Okay, so there's 0 possibility of being at 2. When you look at 1, okay, this one right here, stepping right, right, and then left, means we go to 2 and then back 1 to 1. This one is right, left, right. Okay, so that means we end up here in 1 again. All right. And then down here on this one, we step left, right, right. Okay, that gets us into 1. And that's it. So there are 3 different ways of getting 1. Okay, so we end up at 1 with that case, or that case. All right, and then it's symmetric the other direction. There are 3 cases of getting -1. Okay, so our question is, can we predict where we would be? All right, well, we can give a probability of where we might be based on these 3 steps. Now, if we try and say, okay, well, what's my average position? What's the the average position of all these? Well, I can say, okay, the average. Well, when we add them up, because it's symmetric, I get 0. Okay, there is equal number of steps and identical steps to the left as there are right. So that doesn't help us, but if we talk about moving away from our original position, it doesn't matter if I stepped left or right. I just want to know how far did I go. So to find that, what we could do is look at x squared. So our final position, so x3, but square it. Okay, so we square it. That gives us all positive. So now I have 9, 6 ones, and another 9. And if I sum that up, I get 24. Divide by the total number, which there are 8 of these, I get 3. Okay? And you might be like, huh, I got 3. The average of x squared ends up actually being the number of steps I took. And that's actually generic. If I took 4 steps, the average of my final position squared would be 4 steps long. Okay, and so in this case, to find out where I am, how many steps, I just take the square root of the average. That bar there means average, so it's the average of the sum of the squares of all those. Okay, or sorry, the average of the squares. All right, and so that's the square root of 3, and I get 1.7 steps. So I would expect myself to be 1.7 steps away. All right, now. If I generalize this, like I said, the average displacement, the distance from position, so I can use delta x, this triangle means a change in. So that's a change in. So how far did I go is proportional to the square root of n in steps. Now, if I say each step has a length L, so maybe a micron or a nanometer, depending on what kind of objects we're looking at. I could talk about a human taking a step of a meter, something like that. But anyway, just if we have some length L, then we just have to tack on an L here, right? But if we go further and we assume it takes some time, some short time delta t, that might be microsecond for a molecule, it might be a second for a human being taking a step. But if we do that, then we have two definitions here. The total time, okay, it should be just the number of steps times the time per step. Okay, and so we can rewrite that to say that the number of steps is then equal to the total time divided by the time per step. All right, now you might be wondering, why are we doing this? Well, if we take this and substitute it in here for n, and then tack on our L to get like a meters or something like that, then we can now express the displacement, how far we've gone, in terms of the total time, which is measurable. We can measure the total time, and then the distance per step and the time per step. Now the problem is, we usually can measure our average. We can actually measure, how far we've gone. Okay, and we can also measure how long it's taken. Okay, but it's hard to know what is the step. For a human stepping on a sidewalk, we could probably measure that fairly easily, and we could probably time that very easily, so we can get our delta t as well. But for a molecule moving, it's kind of hard. It's really small, and really we don't know, because it depends on how good our camera is, how fast our camera can take. So sometimes it can be really hard to see those steps. But since we can measure this and this, then we can define a parameter that we call the diffusion coefficient, okay, that kind of describes the combination of those two. So if we define d to be L squared over 2 delta t. Okay, now you might wonder why. Okay, we can see that the square is going to come, so we can insert it in here. Okay, and the delta t is already square rooted here. Okay, the 2 has some different connections. Okay, there's some differences there, so we're not going to worry about that 2 now. It's just to make sure, it's just allowed to be consistent with some other theories that use diffusion. Okay, but by taking this definition and plugging it, in for L and delta t here, you can do some algebra to do that, and you'll end up with the average displacement as being equal to the square root of 2 times this diffusion coefficient times this total time. Okay, so now I can find the diffusion coefficient, which is a physical parameter. It depends on how big the steps are, which is dependent on the object, the molecule, the human, whatever it is. It's a parameter that describes that characteristic, and the time, which is also characteristic of the molecule or the object. So d, this diffusion coefficient, there should be some diffusion coefficient for a certain molecule in water, or a certain molecule on a microtubule, or something like that, or perfume in air. That would have a diffusion coefficient. So we can find these diffusion coefficients, and if we can find it for a class of particles, then we could predict how far it will go. So if you open up a bottle of perfume, and we already had calculated from previous measurements the diffusion coefficient, then we can predict how long it will take before someone across the room smells it. Okay? So this becomes an equation that we can now do experiments with to test the material itself. What are those parameters? And we'll see that this follows through with molecules moving. Now, something we're going to have to note, that this came assuming we were taking steps just left to right. So it's called a one-dimensional random walk. Now, what's cool is that with the definition of D, that you can translate this to be in 3 dimensions, or 2 dimensions, like in a plane, or 3 dimensions, and you're going to get the same thing. It's just instead of a 2, you'll get a 4 for 2 dimensions and a 6 for 3 dimensions. Okay, now we'll focus most of our mathematics on this one, but we can know that the other ones are only different by a factor of 2, 4, or 6.